Okay, what is the angular displacement of each of the following hands of a clock in 1 hour? 100 seconds. We don't like hours. So in 3,600 seconds, what's the angular displacement of each of the following hands of a clock? The second hand. The second hand, I think we did. Angular displacement. What two equations has angular displacement in it? Theta equals. Does that look familiar? Theta equals WIT plus 1/2 alpha t squared.
Yes.
In a linear world, what is this equivalent to?
D equals V naught T plus 1/2 AT squared.
Good. And what's the other equation we can use to find angular displacement? Think linear.
Omega final squared equals omega naught squared.
Good.
Plus 2A
Two.
theta. 2 alpha theta.
Alpha theta.
Yes.
Make sense? This one, we got to use that because we have time, and time is not in this one. So we can't use this. We got to use this. It's the same logic we used in our September and October of our junior year. All right, it's the same logic, except now we're talking about things that rotate and the Greek alphabet. Same thing. So alpha equals WIT plus 1/2 alpha t squared. What's the acceleration of the second hand as it goes around the clock?
Clock doesn't accelerate.
The hands don't accelerate. It's doing the same motion, so that drops out. Agreed?
Yes.
So alpha angular displacement equals Wi times t. The time we know is 3,600 seconds. What is the angular velocity of the second hand? Angular velocity equals?
Well, it goes around 2 pi.
The complete revolution is how many radians?
2 pi radians.
2 pi radians. And how long does it take to do that? The second hand.
60 seconds.
1 minute, 60 seconds. So now we got 2 pi times 60 divided by the time, 3,600.
Yes.
Agreed? That's a pi. Make sense?
Yes.
So that comes out to about 376. What are my units of theta?
Degrees. Radians.
Radians. Damn. 376 radians. Is that positive or negative?
Positive. Negative.
Because it's
Clockwise.
negative 376 radians. Make sense?
Yes.
Okay. Now, the minute hand. Same thing. We got to use theta equals WIT plus 1/2 alpha t squared. The minute hand does not accelerate. Its velocity is constant. So, theta equals, so the angular displacement of the minute hand has to equal, the time is still 3,600 seconds. What's the angular velocity of the minute hand? It does one complete revolution in how many seconds?
60 times 60? 360?
3,600.
Times 3,600?
Times 3,600. They cancel.
2 pi.
2 pi.
6.28.
6.28. What are the units?
Radians.
Radians.
Negative.
Negative because it's going?
Clockwise.
Because it is
A clock.
a clock. Now the hour hand. Theta equals WIT plus 1/2 alpha t squared. Does the hour hand accelerate?
Never.
It does a nice, constant, boring trip around the clock. So theta equals, and don't shout this out, WIT, everyone gets this wrong the first time they look at it. What is the angular velocity of the hour hand? It does one complete revolution, and one complete revolution is 2 pi radians. How long does it take to do, Mrs. Davidson, how long does it take the hour hand to go around the clock one whole time?
12 hours.
Ooh, she got it right.
I got it wrong.
Almost everyone says
24 hours.
24 hours, but there's two 12-hour periods in a day. So that's got to be 12 times 60 times 60. Agreed? Times, what was the time?
3,600.
Everything's in hours here. So this 3,600 and that 3,600 can cancel. That becomes pi over 6. Agreed? And what are the units?
Radians.
Radians. So that's 3.4. It's like a half a radian.
0.5, yeah.
Half a radian. And is it positive or negative?
Mom, what do you think?
Negative.
It's negative.
Because
That
it's
would be
going
correct.
clockwise.
It is. Number 6, a bicycle wheel with a radius of 38 centimeters. What do we not like about centimeters?
They're not meters.
So that becomes 0.38 meters. Is given an angular acceleration of 2.67 radians per second squared by applying a force of 0.35 newtons on the edge of the wheel. What is the wheel's moment of inertia? So torque equals I alpha. We're looking for moment of inertia. So that's torque. Wish I had my whiteboard. Smartboard. Torque divided by alpha. What's the, let's see what we got. Bicycle wheel, radius 0.38, and has a force of 0.35. So the torque has got to be 0.35 times the force.
0.35 is the force.
0.35 is the force, thank you.
0.38 is the
And 0.38
vertical,
is the distance.
perpendicular.
Thank you. And now we got to find the angular acceleration. They give it to us, 2.67. Well, this is an easy one, too. All right, what's the moment of inertia? It's just that divided by that. That comes out to about 0.05.
Just 0.5.
0.5?
Yeah.
You sure?
Nope. You're right. It's 0.05.
I was right and you were
Wrong.
Okay. So it's 0.05. What are the units of moment of inertia?
Kilograms. Meter squared.
Kilograms meters squared.
Time.
Rotate at a constant 5. Is it still working?
Oh yeah, you're good.
A torque rotates at a constant 5 RPMs. How can I quickly change that to radians per second?
Times 2 pi over 60. So
Pi over 30.
which is 0.1.
0.1. So it's about 0.5, 0.1 times 5 radians per second squared, right? If you do the math, you may come out to 5.02. Close enough. What is the angular velocity? What can you say about a point at the axis at the rim of the rotating wheel? So here's the wheel, and it rotates at 0.5 radians per second squared. Now this is an important concept. If you're right here, let's call this point A and this point B. Which one has a faster angular velocity?
Point
Point
B.
A or B? They are both
The same.
rotating at,
0.5.
right?
Yeah.
They're both going in lockstep. They're both doing the same number of RPMs per minute. They're both doing a half a radian per second squared. But let's say this is a turntable, and I have a coin here and a coin here, and I start it up real slowly, right? And it's turning at they're both going at 0.5 radians per second squared. But what if they both slip off at the same time? Which is going faster, A or B?
A. B.
When you're on a merry-go-round, where do you get the faster ride? Closer to the center or further away?
Further away.
Further away. So that's the big difference. They always have the same angular velocity. They always have the same RPMs. This one does not have 40 RPMs and not have 20 RPMs. They're both doing the same number of RPMs. What's different is the linear velocity. The further you are away from the center, the faster you're moving to keep up with this. So that's the big difference. Angular velocity is constant. Linear velocity is proportional to what? Linear velocity increases with distance. So linear velocity increases with the radius from the center. Now I've taken a lot of physics tests and I've seen a lot of physics standardized tests, and almost all of them ask or try to make you define the difference between angular velocity and linear velocity. Okay?